Sorry, I was logged out for a while. Where's my distance? Did I close? Okay.
Welcome back, sir.
Okay, thank you. Yes. Yeah. Yes, sorry for that. The network was just. Yes, I was talking about spacing and sperma. These were biologists, they were genetics. Fisher also, if you remember, I said Fisher was the person that wrote statistical table, was a genetics also. So most of the people that made way early that developed statistics were biologists. Then we have some social scientists also that follow. So because we needed, I was explaining Charles physics, chemistry, those ones they are fixed. But when it comes to biology, if we even talk about blood pressure, the way blood pressure here, very here, is different from America. So if you measure some of those function physiology, it may not be exactly the same. The value you get in America, Canada, and Britain will be different from our own because there are a lot of variation when it comes to biology. The same thing with social science. Look at discrimination now. The way we perceive things differ across, unlike the physics and chemistry. So the research over the year that have been in biology and social science, they have to battle to really know how to, when they do their research, that whatever finding they are giving is not due to some extraneous variation. And that's why over the year they develop statistics. So let me just tell you that if you're a biologist, that's why if maybe a mathematician or somebody that just went to school to study statistics, even teach you statistics, it will be dry. You just be writing X and X and that has no meaning. But if you're a practicing professional, especially a biologist or social scientist, that you have used this statistic, you'll be able to put life in it. You'll be able to give example how it works. So it's the same thing here. So we want to look at, we've described this correlation now. Let's look at the data. This data set, this one I'm showing here, we'll use it to demonstrate both Pearson correlation and Spearman correlation. So, and be ready to share when it is time. But let's first of all see how do we use and to compute them. Here now you are looking at 15 people. You measure their height and their pulmonary death space. Height. So height is measured in centimeter here, and the pulmonary death space is measured in mil. So the pulmonary death space, death space, for people that are not health people, pulmonary talk about lung. So death space that when you breathe, there are some area that part of the lung that we hear will not reach. They call it death space. So it's vary with people. So the people that do exercise a lot now, their own they will have reduced. It may not be reduced. Then it vary with age also. It can vary with many other things. So here now for 15 people, they measure the height, centimeter, and pulmonary death space in male. So look at the value. Let's say because we don't let us talk about anything. Just we know that the height is the X, and the pulmonary death space is Y. Just have to denote it by different things. So how do you get, if you remember the formula for Pearson correlation, we just say R is sigma X minus S bar to Y minus Y bar over square root of sigma S minus S bar square, then square root of sigma Y minus Y bar square. So here now, what do you need? You need X, but you already give you X and Y. You need X bar, which is mean of X and mean of Y. So, and you need to now put, you need the deviation, which is X minus X bar. You need that. Those are the things you need here. So look at what we did now. The first two row, column rather, we put S and Y. We calculate the mean. If you look at it down, we have calculated the mean for somehow. We'll have put the mean there. Though, yes, there's a way you can, but I think we calculate the mean there, and I think we have calculated the mean. And now what we just do is to, okay, we look at it in this blue table, the first table, we have already put the sum and the mean. You know, you add everything together, divide by the 15, it gives you the mean for each of them. So this second table, now the third column now, X minus X bar is not showing very well. It's not just S minus S bar. So you remove the mean for the height, which is 144.6 from the value there now it gives you. As usual, because as well we have arranged all these in ascending order the way they are. At least for the mean, it's arranged in ascending order. And for the height, it's arranged. Is it actually arranged? Yes. 110, 110, 120, 120, 131, yes, it's arranged in ascending. So the issues that initial value are confessed. You see that those ones that are less than the mean, the smaller one, they will give you negative value. Can you see? The same thing you do for Y, which is the dead space, pulmonary dead space. So if you look at another thing you need to do is, so in the, if you see the numerator of the formula, it multiply the X bar minus X minus S bar times Y minus Y bar and sum it together. That's why you have in the words, that's what you now have in the, is it fifth column now? So there X minus S bar and Y minus Y bar, you multiply them. It gives you, you know, you see that if both of them are minus, it will cancel out. That's what you can see there. The sum, it does not cancel out. It depends. So when both X, Y minus Y bar are negative, when you multiply both of them, they will cancel out. So X minus S bar multiplied by Y minus Y bar is what you have in that column. Then you now have the column like X minus Y X bar square. If you look at the denominator, you see X minus S bar square and Y minus Y bar square. We now square the X minus S bar, also square the Y minus Y bar. You add everything together for each, add them. So that's why you see sigma, sigma, sigma. So we also have the square root. If you look at it now for the, when you have added everything together now, for X minus S bar square and Y minus Y bar square is the square root you use in the denominator. So that's why we also calculate it down. It just fits in the into the formula. R is equal to 5426.6. That's addition of sigma, that is addition of X minus S bar times Y minus Y bar. Then over this one, the square root of X minus S bar square, which is what we have here, 72.46792, times the square root of Y minus Y bar square. So we give you, though normally, if we are to give you an exam, this is how we give you short to calculate it. I can't remember when I gave it to a student to calculate, but the issue there is just for you to know the logic. So the Pearson correlation is 0.84681. So you may ask, is it positive or negative? So you can answer. Is it positive or is it a positive or negative correlation? You can unmute and answer.
Positive.
Yeah, it's positive. So then the same to test whether the association is merely apparent and be given by chance. There's a way is it this one now is just to calculate the R, but to test if it's significant. So there's another one I use T, but look at the own formula for T is different for what you know. If T is equal to R square root of n minus 2, 1 minus, so it gives you the value. So from this one now, you check better. The issue there is that it's just for academic purpose. We don't use the p-value to interpret correlation. So let's talk about Spearman rank correlation before we run, because it's the same data I want to use to run it. So a plot of data may reveal overlying point well away from the main body of the data, which will unduly influence the calculation of the correlation coefficient if it's Q. Alternatively, the variable may be quantitative discrete, such as count, e.g. number of children, other category such as likelihood. Can you see? So in a situation where even the one that is you follow normal distribution, you may have some outlier, or we are using something like likelihood scale that I've said before, Payne score, all these likelihood scale for agree, disagree, all those, or maybe a level of verification, anything that is ordinary. I just give arbitrary number 1, 2, 3, 4, 5. You give arbitrary rank. A non-parametric procedure due to Spearman is to replace the observation by their rank in calculation of the correlation coefficient. So the same, if you look at it, the same data set. But because the formula differ, this one is, though they call it R square, you can call it rho, but RS instead of just R. That's Spearman correlation. 1 minus 6 sigma d square over n to n minus 1. So all you need to, what do you need there? You need the difference. This is the D. So you have to first of all rank first. It's the rank you are looking at. It's not the value. You know, when we did the non-parametric counterpart of student of t-test, it's the rank we use. So here now, as you are reading the height and communal test space, you rank height. Height, that is the smallest one, should be number 1, you list letter. The other one, you rank the other one from the smallest also. Now, I remember whenever there are 2 tier rank, you have to give, like this one, we have the one that's supposed to be number 5 and number 6, they are the same value. So what you do is to now say, both of them are 56, 56. You now calculate the average, 5.5, you give to them. In that situation, there won't be number 6 rank. You now continue from number 7. Can you see? So continue like that. So that's for the dead space now. Yes, there are some time values. So after you have done that for each person, you now look at the difference between the rank. You minus 1 from the other. Here now we try to minus the height rank from the dead space rank. What we minus now, it gives you, we now square, that's the difference. You now square the difference. You know what the square does for you to remove the negative stuff. You now sum it together, which is sigma d square. Can you see 60.5? Every other thing is the sample size, n minus, which is 15 minus 15 square, which is 225 minus 1. So we give you 0.892. So which one is higher? 0.892, this one is 0.84. So even the rank correlation, that one is higher for the same everything. There's another form which this Kendall, don't bother with that, because most of the time we don't use every Kendall. So do I have an example there? I think it's the same. Is it the same example? No, different example. So let's just, then this is how to compute by serial correlation. That's what we're doing. Let's try to, before we come back to talk about how do we interpret. We can actually talk about the interpretation. Let's talk about it before we run it. So how do you interpret? Though there are different people come with different ways of interpreting. I've already told you, if you do the correlation, if the computer will give you p value, it's useless. It's useless for interpreting, and the reason is very simple. If the sample size is very large, a small correlation will be significant. If the sample size is very small, a big correlation will not be significant. Can you imagine? Imagine that you have a correlation in this one is 0.12, and you have another correlation is 0.45, and that 1,2 is significant. The 0.45 is not significant because that 1,2 we're having about 800 when it comes to sample size, while the other one we're having about 70 because the sample size is very small. So when the sample size is very small, a big correlation will not be significant. When the sample size is large, a small correlation will be significant. So that's why the intelligent people now came with the idea, how do we interpret correlation? So now look at the strength and the magnitude. When it is perfect, we know that all of them are on the line is 1. So if it can be positive or negative. The same thing, if it is strong, 0.75 to 1, it can be positive or negative. Moderate is 0.5 to 0.75, positive or negative. Weak is 0.2 to 0.5. So if you look at it, another one, different people come with different way of interpreting it with reference. Look at Guilford method here. Guilford rule of thumb. See R, see, less than 0.2, negligible relationship or correlation. From 0.2 to 0.4, low relationship. 0.4 to 0.7, moderate. 0.7 to 0.9, high. Then very high, anything greater than 0.9. But when it is 1, it's perfect. Can you see now? So when you are interpreting, if there is a correlation of 0.23, now say there is a low moderate, or you can say a low correlation between a low positive correlation or negative correlation. You have to, it depends on the sign on it, whether it's positive or negative. So let's try to run all those other ones about correlation I have here. They are very advanced, and I don't want to bother you with it because it's not for beginner. When you are just learning, you confuse you the more. So it's when I was doing the workshop, many of them. So people have received correlation workshop and are now dabbling into some advanced concept. That's why we have the partial this thing. Though I will still talk about what the meaning of bivariate partial explain. So let's somebody, there is this height and pulmonary death space who will share. National Tuberculosis Conference. Can you share? Do you have everybody has data now? Height and pulmonary death space. Who is sharing? Messi or Asmao? Or Mukhtar? At least we see you today. Can you share?
So I want us to share.
Somebody should share, sir.
So I want us to share.
Yeah, the data. Height and
Which one?
height and pulmonary death space. Who is making us space? Height and pulmonary
Okay.
death space.
Okay, I'm sharing now.
Okay.
It's trying to open up.
Okay. Yeah, that's great. So you go to analyze. Analyze. Go to analyze. Analyze. Go to analyze. Go to correlate. Correlate down. Bivariate. Click on it. So move the two there. Just move the two. No, it's something that is very easy to run. Move it now. Move them. Move both of them. You see by default, it put Pearson. You can also click on Spearman. Also click on Spearman. Check on Spearman now, is there. Where is this low? Okay. Click OK. Click
So it's
OK.
actually okay.
Yes.
Pearson and Spearman.
Yeah. Leave that candle. So you have to share your output now.
Okay, sir.
You have to stop sharing this one. Share down. Yes, thank you. So if you look at the first one, the first table is parametric, that's the Pearson. The second one is the non-parametric, that is Spearman. So you see, both of them are arranged in the same way. If let's say we have even about 3 variables at the same, let's say we have age there, everything, we can run all of them correlation together. The way it will arrange it for you is that it will arrange it vertically. If let's say we have age, height, weight, pulmonary, it will arrange it vertically and arrange it horizontally. So if we look at this now, you see one along the other. You see that one is correlation between height and height. Can you see height and height in meter? You know, if height and height correlate with itself, it will be 1. The other one you see at the lower right corner is correlation between pulmonary dead space and pulmonary dead space. But the other one is what you have is 0.846 is correlation between height and pulmonary dead space. The other one, pulmonary correlation between pulmonary dead space and height. You know, it's the same thing. So because computer is not human being, so that is the only way we can bring it up. So it will give you double result. But it's the same thing, 0.846. So if you look down, the same thing for this thing, the same thing for non-parametric. You see this. I just want you to, though it's not appropriate thing, go back to analyze. Since we have serial number, hard serial number, of course you cannot use correlate serial, but I just want you to see the way it arranges for you. Go.
So is it from here?
Yes, you can do it from there. Analyze from there. You can access from there. Go to the same correlate. by varied. So move that serial number, move it there. Let's just assume that serial number, you know it's number also. Let's assume it's a variable, but your phone you cannot do serial number. It's arrangement I want you to see. Click OK.
Let's stop sharing and share you.
No, it's showing us. I know you are working from there. We can see it.
Okay.
Can you see what it does now? You have scroll down. Oh, you have gone to Can you see what it does now? It's assumed that look at it. You see the 111 along the diagonal. So that 1 along the diagonal is correlation between height and height. It be 1. The next one, correlation between dead space and dead space. Correlation between serial number and serial number. Can you see now? But the one you now have along half the diagonal on both opposite sides, they are mirror image. It's just one of them you use. We usually use the lower one when we are drawing our table. We draw it the way the lower one is. So you see along the diagonal, you see 1. Even if they are about 7, even more than that, that's the way to arrange it like that. So you see what is telling you now is that you see correlation between pulmonary dead space and height is 0.846. Correlation between serial number and height is 0.99. And then correlation between serial number and pulmonary dead space. Can you see? So somehow it will give you. So these 3 values, one will be between pulmonary dead space and height, one between height and serial number, one between pulmonary dead space and serial number. Can you see that? That's the way correlation is being arranged. And when you are drawing your table, that's the way you put also. Of course, the one off the diagonal hop, the right up, you don't label it like that because it's the same thing. If you look at it, it's the same thing. It's a mirror image. So that's the way correlation is being arranged. I don't know if you understand me now. So the same thing, whether sperma and so whether you do sperma or spacing is a function of the type of variable you are dealing with. You use the one that follow normal distribution. Yes. Any question? Any question? So it's very simple. No question. You can stop sharing.
Yes, sir.
So there's the lecture of today, which I will just quickly give it, because what I gave now is what was supposed to have on Monday, but you know, the lecture is not so, because the way we have it today, we will not even demonstrate anything. It's just for us to understand one concept, a concept we call potential error in measurement. And that, if you look at our timetable, that's what we slate for today. It's very short. So let me just quickly talk about this correlation. I try not to have two major introduce new topic when you finish one. Like for example, now, when you finish correlation, you can get moved to a related concept, linear regression. But that won't take a longer time to conceptualize. So it's better something you start afresh, not when everybody is tired. But let me quickly give this potential error in measurement so that we know that we are done with it. So somehow, it has shortened the number of days by 1. That is, like now that people refuse to even come. So let's quickly talk about this potential error in measurement. You need to understand it for you to understand why we do regression, why we do multiple regression. Because next lecture now, we have to go to talk about regression. So the logic behind potential doing regression is this potential error in measurement that open your eyes why you do. So there must be reason you do something. So let's talk about error. You have heard of error when you are doing research, or when you are doing measurement. The difference between a measure quantity and its true value is the error. If you go and measure somebody, you measure somebody's weight now, you may say, oh, 74. But the true value may be 76. or 72 or 75. So that difference is the error. The same thing, as the way it's applicable to just measuring something. It's the same thing. If you do research, you want to know the prevalence of hypertension, and you now say, oh, the prevalence of hypertension is 25, and in real life is 28. There is an error. The difference is the error. I don't know if you understand. So this issue of concept of error is applicable to whether you measure something or what you are measuring in your research. Whether you measure something in the process of data collection or the aggregate estimate you are going to make in the research. Once what you get as a value is not the real value, there's an error. The difference between them is the error. So x is equal to t plus error. That is, the value is the x. What you measure is the t. The difference is the error. So so if you look at it now, the difference can be positive or negative because sometimes what you measure may be higher than the real value. That's why that difference is minus. Or what you measure is greater than the value. Okay, no, what you measure, if it's less than the value, this error is positive. But when it's greater, yes, if it's greater, it's negative. So this error you see has two components. Can be random error or systematic error. So in reasoning, X is equal to T plus random error plus systematic error. We talk about random error and systematic error. So let's talk about what is random error versus systematic error. Random error occurs when a value of the sample measurement diverges from that of the population value due to chance alone. Chance, not because of the way you measure it, but it just happened like that by chance. That is mean of random error. Random error causes inaccurate measurement of association. It's the same thing. You measure, you went to do prevalence of anemia. You now say it's 31 among these children under 5 in this community, and in real life is not that. If that component of the different, the error, that is just due to not because the way it just happened like that, is the random. So the systematic error or bias occur when results differ in a systematic manner from the true value. Systematic manner means that the way you carry out, research is systematic. So there are some laid down rules in research, step by step. So by the time, if you are not stringent in the way you carry out, if you are loose, you don't follow the protocol very well, the right thing, it can lead to error. The error due to the way you carry out research is systematic error. So the error now, so whatever you estimate, if it differs from the real value, the difference may be, some of it may be due to random error, some of it may be due to systematic error. So overestimation or underestimation of parameter of interest due to way and manner the study was carried out, that is systematic error. It is error caused by factor other than the causes of random error. So let's look at it. Just to summarize it, errors. We have random error, systematic error. Under the random error, 3 things can cause that random error, even though it's due to chance. That is not due to you, the way you carry it out, but due to something anyway. So individual biological variation, sampling error, and measurement error. So I don't know if I measure individual, yes. So let's just quickly look at it there. So individual biological variation, sampling error, or measurement. Random error may never be completely eliminated since we often study only a sample of the population. So it may not, there is sampling error now. This sampling error is not because of the way it's not the type of sampling, no, because the way you sample, we are going to get to it. It's part of systematic error. It's the selection, it's a part of selection bias, the way you sample. But this sampling error they talk about, for the fact that you did not carry out the research on all the elements of the population, that you take sample, it has reduced sampling error. Because In as much that you didn't attend to all the element population, whatever estimate you get can never be equal exactly the same thing as parameter. So that difference is the sampling error. Because it may be due to saying yes, that component of error is due to sampling error. And you can reduce it by increasing your sample size. If you increase your sample size, the value will be closer and be closer. So random error. So even in situation when we study the whole population, in case of finite population, random error may still occur from individual biological variation and measurement error. Can you see now? If you study the whole population, yes, there's no more sampling error. But standard random error can still occur because we have other two causes, individual biological variation and measurement error. So individual biological variation occur and no measurement is perfectly accurate. For example, now measure, even though we can reduce it, okay, we say measure this in height. We see how you measure it. We have to measure it again, over and over, so that it's accurate. It's also. And another thing about individual biological variation is if you, for example, now you want to know the cholesterol or maybe fasting blood sugar, you ask people not to eat from 10 o'clock. Apart from the fact that you don't know how many of them are they saying the truth, who they eat after 10 o'clock, or if somebody, even though the person that had by last 6 o'clock is different from the person that had last 8 o'clock or 9 o'clock or 9:50 something, or that exactly 10. And the volume of what they eat and type of what they eat, a lot of things. And when you down, they come, you want to do the study. Sometimes the person you collect the blood pressure, blood sugar, and blood sample from by 8 o'clock is different from the person the measurement you got will be different from the person you collected by 9, by 10. They say by 11 you stop because you don't want to go beyond by that time lipogenesis. The person is hungry and the glucose in the liver is being released to the body. For the person glycogenolysis. So in that situation now, the glucose is being released. At the end of the day, it will increase. It may increase it. Can you see now? So even the person, if you take the blood sample from someone by 8 o'clock, what you will have got will be different from if you take it by 9 o'clock. And as they are coming, you attend to that. So that was why we say that when it comes to biology, it can never be exact. And behavior, it can never be exact. So that is where individual biological variation comes from. Sampling error is usually caused by the fact that the small sample is not representative of the population variable. Individual variation always occur, even if you take measure, because the measurement is never accurate. So how to reduce random error? The best way to reduce random error is to increase sample size. I've said it. Measurement error can be reduced by stringent protocol. That is when you are taking the measurement, take it very well. If you look at it, one of them is measurement error. That is when you measure, you take the measurement. If you say measure the weight, measure the height. Even if it is finger clubbing you are assessing, the way you assess it. So stringent protocol, this way that you can reduce that measurement error aspect of the random error. So making the individual measurement as precise as possible. So let's talk about systematic error. Researchers have different, okay, if you look at it, that's something. The aspect of systematic error is selection bias, information bias, and confounding. Though we have over 30 of those things that cause those things, but they can be classified under these three: selection, information. So systematic error is also what we call bias. When you say bias, systematic error. So selection bias, information bias, and confounding. Now, researchers have identified over 30 different biases, and there are different approaches used to classify them. However, the approach which is often used is to group all the biases into 3 general categories: selection bias, information bias. So, source of error in epidemiological research, okay, just this one. So I've said it before. So selection bias occurs when there is a systematic difference between characteristics of the people selected for a study and the characteristics of those that are not selected. So this is where sampling, the way you sample. If you don't use systematic sampling, if you don't sample, use the appropriate sampling method, you are introducing selection bias. It's not sampling error. Sampling error is due to the fact that you take sample, you don't take the whole population. But this one, selection bias, the way you do your sampling, it's sampling technique. If you don't, it's not done appropriately, the selection is not made appropriately. So you go to see that systematically, the people that are selected will be different in some characteristics than the people that you select, and it will affect your use bias. I usually give an example. I say you want to study the proportion of Igbo in Lagos. And you will now, if the value is 20%, for example, and you now go to Ladipo, go to Isolo, go to Festac, that's why they are populated. It will give you even as much as 40%. That will be a selection bias. If you now go to Diaraba or go to all those places that they are not, there are some places they are not there much, it will be lower also. So can you see the way you, so you have to balance out. Sometimes there are different ways we talk about how do you reduce bias. Now, an example is when participants select themselves for a study. Just, let's say I want to participate. So it may be, maybe I've heard that there's one benefit. So those people that need benefit from that thing, maybe it's the same in some context. They will say, we have got to be part of the study. Those who choose to participate may be different in some important way from those who choose not to participate. So look at selection bias. Selection bias occurs when you are selecting your sample on your data in the wrong way. So, then information bias. This is also known as observation or classification or measurement bias. It's different from measurement error. Measurement error is part of random error. The way you measure is different from measurement bias. So this measurement bias is what we call information bias. Selection bias is the way you select your sample. Then how do you elicit information from them? For example, now, there is one problem we usually have with recall bias. It's a form of information bias. It's usually a problem with case control study. Because case control study, you select the people that have cases. You recruited the people that have the disease. You also recruit people that don't have the disease. So when you are eliciting, you are asking your question, the way you ask the question. In a way, it's the way you ask the question, or even the question itself. Somebody that is a key, because you are asking, it's the question you have the people that are case and control. For the cases, if you have somebody that has, like, for example, varicose vein now, and you are asking if the person has used OCP, because you are studying effect, maybe the OCP has contributed to the development of varicose vein. And the people that have case of varicose vein, you are asking them, they will likely remember than the people that don't have varicosity. Because the person that has the problem will say, and did you use OCP? Yes. You'll be thinking, can this be because of my problem? Yes, I use it too. Even if the person didn't even use it I think I used that thing for long. He will likely remember that he used it. But the person that doesn't have problem, even if the person has used the OCP very well, because you are disturbing that person because he just decided to participate in your research, he doesn't have problem. You are just asking, I don't know. No. You will know, even if you are using mail, you don't remember. So it's a form of recovery, it's a form of decision bias. There are different ways. For example, now if you are doing randomized control trial and you put some people on a placebo, put some people on the active drug. If they know, those people, they know that they are taking as active drug. And the people that are taking placebo know. You didn't blind them. You will get information bias because the people that are taking, because you are measuring the effect of the drug, maybe one of the effects that make them sleep very well. Maybe insomnia is one of the problems the drug will solve. So the person that if he knows that he's in the active drug group, if he has, did you sleep? If he is, I sleep. Because you know that's your expectation. What you want to know if that drug works, if it's sleep. So they will say that even if they didn't sleep, well, they slept. But if the person that is in a placebo group, if the person sleeps, did I sleep? I don't think I sleep like that too. Can you see? So the way you elicit information is called information bias or observation bias or classification bias or measurement bias. This occurs when individual measurement or classification outcome or exposure are inaccurate. They do not measure correctly what they are supposed to measure. Then how do you prevent? Prevention of selection bias, sample selection criteria, high response rate, high rate of follow-up. Then prevention, when it's always sample selection criteria, you have to talk about your sample and sampling method very well. Prevention information by clear definition of what you are looking for, good measuring method, blinding. For example, now, for the randomized control trial I talk about, you blind them, you don't know, they will not know which one did they belong to. They will not know, are they taking active drug or placebo. So if they don't know, they will give you, they just know that they are doing study. They know that there are two treatments they are giving, but it belongs to one. So they will just be objective. But that is single. If it's day, it's only day. I don't know. And you are asking the investigator, you are asking the question you know. You may still cause information bias. Because somebody that is in an active drug group and the person doesn't know. When you say, did you sleep well? You say, I didn't sleep, I slept well, or I didn't sleep well. Because you are expecting, because the person is in active drug. Are you sure? That one, that's okay. Well, maybe he's expecting me to, maybe, I slept. Can you see? Because the person knows the group, which that is single blinding, because it's only in single blinding, it's only the participant that don't know. So in that situation, they just the investigator know. It can still be biased by the way it's asking the question. Whereas the person that didn't is in placebo group, when you are asking questions, since you know that it's a placebo, did you sleep? I slept. Are you sure you slept? Oh, well, I didn't really sleep like that. No, the bias is already. So if you do double blinding, blinding means both the participant and the investigator, they don't know. So in that situation, they cannot. So also even at the level of analysis, if you do only double blinding, the person that is analyzing, maybe me, as a statistician, I'm the one analyzing. You have already told me that this first group is the placebo, this one is the. If I'm running it, the thing is not. Wait, so I begin to share what happened to this data. It's not. This is what we expect. If you want to blind the person, also, you can do triple blinding. Even the statistician that is running it does not know which group is the. It just know that there are two groups. They will not know either a group 1 or 2, which one is placebo, which one is this. That's triple blind. In that situation, until they finish the analysis, they will now open, they see the report, they now open the seal. You really know for people to know which group is actually active ingredient, which group is placebo. So standardized procedure and control, quality control, those are the main ways. So the last type of bias is the confounding. So confounding occurs when a variable is associated with the exposure and it affects the outcome. But it is not an or intermediate link in the chain of causation between exposure and outcome. This diagram will explain these two sentences for you. Look at here, where the relationship we are looking for is exposure, disease. Exposure go to a disease. Now, this confounder is another variable. You see, that confounder is another exposure. There is a risk factor to the disease, can cause the disease, but that's not what you are studying. You are studying this one, exposure to the disease. You are looking at the exposure and the disease. But this confounder is a form of thing that cause the disease also, but it's not what you are studying. But it's association with the exposure also. Can you see? Both of them. Let me give an example. If let's say you want to study does coffee, does it affect heart disease? Coffee does it cause heart disease? So the relationship you are looking at is between coffee and heart disease. And here, you know that alcohol also can contribute to heart disease. Is another problem with heart disease. It can lead, but you are not studying whether your study is not the relationship between alcohol and that. Your whole study is about coffee and heart disease, not alcohol and heart disease. Okay, let me use tobacco. You know, coffee and heart disease, then tobacco. So the tobacco also causes heart disease, the way coffee may cause heart disease. But you are not studying tobacco, it's coffee you are studying. There is an association between coffee and tobacco in the sense that both of them are substance use. In the sense that somebody that is taking coffee will likely take tobacco than the person that is not taking coffee. And somebody that takes tobacco will more likely take coffee more than the person that does not take tobacco. We are not saying that everybody that take coffee take tobacco, or everybody that take tobacco take coffee, but the person that is taking coffee, if you say coffee, you are taking coffee, to you are not taking coffee, the person that take coffee will be more likely, more of the people that take coffee will more likely take tobacco. If you look at people that take tobacco, not tobacco, the people that take tobacco are more likely to take coffee. So in that sense, there is a parallel association between, they are related, somehow, just like the way correlation between exposure and between alcohol and between tobacco and coffee. But in this relationship between coffee and heart disease, tobacco is a confounder. So why they say, if you can look at the first sentence, this occurs when a variable is associated with the exposure and it affects the outcome. But it is not an intermediate link in the chain of causation. This second sentence, what it means that it's not as if maybe if you take coffee, it will make you to take tobacco, and tobacco will cause addiction. That one is a different thing. In that situation, if you want to study if coffee is affecting heart disease, you have to study through tobacco. Because if the way it works is that coffee will make somebody to take tobacco, and tobacco will cause heart disease. That's second sentence. It's not what is happening now. Coffee itself relates to heart disease. Tobacco itself relates to heart disease. And both of them, the coffee and tobacco, they are somehow related. That is the confounder. Now, if we are studying, let's say we are studying whether the relationship between tobacco and heart disease is the same way coffee will be a confounder. So whether something is a confounder or not, it depends which of them is a confounder. It depends on what you are studying on ground. Most of the time, social demographic are confounders, and that is why we usually, any study you do that social demographic. You talk about age, sex, marital status, education, level of education, employment, and some other things, year of experience, and many, many other things. Number of children in the household, those things, they are confounder in the sense that somehow, with that particular thing you are looking at, they may be related to it also somehow. For example, age now. If they say heart problem, hypertension, as people are becoming age, they may likely have it. And if you go and do your study, you say you want to see what is the relationship between employment status and heart disease, the type of employment, the type of study the work you are doing, and lung disease. And whereas there are some confounders, sex, age may be related to that problem. So they serve as confounder. So relationship between coffee drink, heart disease, it's all very big for tobacco. That's what I even explained there. I think I have explained it. Coffee to heart disease, it's all very big tobacco. So the same thing, relationship between alcohol use, lung cancer, and third variable is smoking. The alcohol and lung cancer. You know that smoking also can lead to lung cancer. And you know that if somebody take alcohol, it will likely the person that drink compared with the person that don't drink, which one will likely smoke? Or the person that smoke and the person that does not, so which one will likely drink more? You see, so there's also association between alcohol and smoking, and you are trying to see how alcohol relate to lung cancer. So smoking is a confounder. The same thing if you want to study how smoking relate to lung cancer, alcohol is a confounder. So method employed during, how do you remove confounder? So the method you use to remove confounder is divided into two. You employ some method during study design at the early stage as you are designing your study, and while some is during data analysis. Why I'm giving this one is because of this during data analysis. So method employed during study designs, randomization, restriction, matching. Though even also them also, even when you do randomization, when you do matching also, when somehow even the way you are you interpret your data also will change. But actually method during analysis are this one. So this one, randomization. So once you do the right thing, because the hallmark of experimental design randomization. Randomization is just selection into experimental and control group just by chance. So you make sure that just by random is do it by chance that anybody that finds itself, it's not because you like the person or the person you feel the case is critical. You find the person that finds himself in the control or experimental, it's just by chance. You just do it randomly. That's randomization. Restriction means that, for example, now this issue of you want to study the relationship between coffee and heart disease, you may say, since you know that tobacco use is a confounder, you may restrict. Anybody exclusion criteria is tobacco. You will not get tobacco involved. Anybody that have tobacco will not be there, whether in experimental, whether in experimental or control group. Anywhere, any of the group you don't want. Even if it is comparative study, there is no experimental. Since you are having more than one group, you make sure that whichever group, you restrict them. That's restriction. So at least if they are not there, they cannot say that they are a factor. They cannot influence. That's another way is matching. Matching means that if you know that, okay, this tobacco, if you recruit somebody into the experimental group, coffee, and is taking tobacco, you have another one that is not taking tobacco. The same thing you do in the control group. Though in the control was tobacco, not tobacco. So you see, both group now, the tobacco use will be spread. You can have equal number of tobacco users. So in that situation, if you analyze the outcome, it may not be because most of those people they have tobacco, they are using tobacco. So that because you go to have some people that take coffee, use tobacco, yes. You have some people that don't take coffee, they use tobacco also. So in that situation, as you have one tobacco case, you have tobacco case in the control group. So those are the user are there. That's the matching. Those are the design. You do at the design stage. But if you have not catered for all these things, you just do it. You may need to do stratification. You need to do statistical modeling. Stratification means that you now do stratified analysis. In that situation, you can analyze separately for people that use tobacco and separately for people that don't use tobacco and compare this. That's what we call stratified analysis. Or the most important, the most popular one is to use statistical model, which is multivariable regression. That's why the multiple linear regression, logistic regression, we'll be talking about next week. Comes in. Any question? Any question?
Yes, sir.
Yeah, go on.
Sir, you talked about ways of reducing random error, which you mentioned for the second and third. That is sampling error and measurement error. But you didn't mention about reducing individual biological variability.
Yeah,
so is there no way to reduce that?
Yes, you can read it, but that one is the one that is the most difficult to even reduce. But you can see, you can only reduce biological variability. You can only reduce the effect. For example, now, when they say they are taking, it's part of stringent protocol, so we reduce it. For example, if you have people to come for fasting blood sugar, you know that you have already told them don't eat after 10 o'clock. You yourself, you quickly take the blood when they come. You don't weigh anything when it's becoming around 11. Don't take again because it will affect the result because the variation is there. So that is the one that is most difficult to control. That is why you cannot completely remove random error. It's not possible. That's the difference between systematic and random error. You can minimize random error. It can never be completely removed, especially due to individual biological variation. But systematic error, you can.
Yeah.
Yes.
Yeah.
So
I'm listening, sir.
Then for me, I still believe in the systematic error that you can completely. I don't believe so. I don't believe in the sense that if you can reduce it very well, but you may not be able to even remove completely. Systematic error. Reason means that the way you carry out your research also may depends on your expertise. Yes or no? All this one ensure you remove confounder. Some people, the extent to which somebody remove confounder, the extent to which somebody remove all the selection bias, vary with individual. It vary with the way they stick to the protocol and the way their knowledge and expertise. So even that one, it's just like say, be that perfect, as your father is perfect. So tell me who is perfect. Somebody cannot touch and say, I am perfect. No. Even though that is a target. That's my own better. Theoretically, they say that, yes, you can remove systematic error. But even another thing is that there are many things that can cause systematic error. So you may remove or you may not remove everything that causes systematic error. It's not only one thing that can cause systematic error. You may be triggered to even reduce and remove some, but you may not be able to remove everything. But we already know that for random error, it can never be removed completely. It can only be minimized. Thank you. Any other question?
So I was thinking one of the ways to minimize the individual biological variability will be based on selection. Let's say for a certain
no. Now that one is not your selection has to do with bias. The way you select is bias. Selection has to do with sampling. Yes, I mean when you say selection, that one is reducing bias. If that should have knowledge that this person may give you something that is non-biased, you avoid it. That's it. In as much that you can control it through the way you plan your study is bias. It's a systematic error.
Okay.
So
thank you, sir.
Welcome.
Good evening, sir.
Good evening.
Good evening.
Good evening.
Okay. I'm sorry I came late. This controlling of confounding, the second one, restriction. I'm not sure I understand it because what you're saying is that you restrict the individuals to certain groups.
That particular confounders you have identified, you ensure that anybody that have that confounder will not participate in your study. That's all. You restrict to the people that don't have the confounder. For example, now you are studying the effect of what do I call it, coffee on heart disease. You know that tobacco use is a confounder. Anybody that uses tobacco is out of the study, whether between among the control or among the experimental, among any of the group. Either it's case control, the experimental study, or cohort study, you remove that confounder. Anybody that has that confounder, you remove it. It's not part of the study. That is a restriction.
It's also possible that while you are trying to do this restriction, you introduce some kind of sampling bias. That's a possibility.
No. The only thing you have is that sometimes you may not, if you restrict too much now, you may not even get, most of the
enough
exactly amount sample size, especially where we are dealing with case control. Case control, you have few cases. We are looking, there are few because it's for rare disease. real problem. If you even get the cases now, you are happy. You want to recruit as many. So if you say you want to be restricting, it may affect your sample size. It's the same way with matching. Matching also, if you want to match too much, you may match for too many things also. That's the problem with matching. You want to match for age. Match for age means that if somebody is middle age, you want another. It doesn't really mean that if somebody is 35, you have to get 35. But they say the difference may not be more than 5. Make sure the age is not so around that. So if you match for age, you are matching for sex, you are matching. By the time you are matching for too many things, you have a type of problem. Even for you to even get your sample size, and for you may be confused also.
No problem.
And those are the problem of restriction and matching.
Okay, thank you.
Yeah, any other one? Okay, there's no.
So I have just a bit of something to share.
Okay,
regarding this individual variability. Yeah, regarding this individual variability.
Okay.
Biological variability. Yeah, there was a time I had this operation for appendicitis. So the doctors instructed that I should not eat beyond, is it 10 p.m.? That is the night before the day of the operation. So I actually didn't eat since 6 p.m. So I even stayed away longer than they requested for. But then during the surgery, there was complications. And I think when they opened me and I was kind of vomiting, there was mechanical action and it caused complication. So it was when I recovered, I heard that there was serious drama and they were yelling at my family members, why did they give me food around 10 p.m.? That the reason for this complication is because I ate. And actually, the thing is, I digest food slowly. I don't digest it takes a while for me to digest food.
Yeah.
I actually ate way earlier. I stopped eating way earlier, and still there was complication because based on maybe it's a theory that if there's a 10-hour or 12-hour interval, then every 2
the food will have yes, and live food.
But
You are
then
supposed
there
to
was
take
something.
live food, yeah.
Yes.
And
Yes.
that's part of the individual variation. You see now, biological variation. That's part of his playing in life. Yes, I mean now.
Yes, sir.
So thank you. Any other one? Any other? Okay, in absence of another one, good night, everyone.
Thank you.
Thank you, sir.
Thank you very much, sir. Good night.
Yeah.
Yes, sir.
Yeah.